We're going to talk about sampling distribution of means. And I know this is a weird concept. When I took statistics, I did not understand this until the third or fourth time that I heard it. Let's give you a really simple, stupid example and see if we can cement this, at least the concept in your head, and then we can move on to some more real world stuff. So we talked about the idea of sampling distribution of means. Let's imagine for a second that our population is very small. Let's say we have a population that has only 5 people in it. And let's say the thing we're trying to estimate is the ability to shoot free throws, basketball. So here's our population. Now, let's say, this sounds kind of real world. We have budgetary constraints. We can't rent the gym. We can only take a sample of n equals 2. Antonio, are you still on?
I'm here.
Can you randomly pick 2 of the people in this population?
Jesus and Lil Wayne.
Okay, that's Jesus, actually, my cousin Jesus. But okay, let's say we had.
Oh, sorry.
Jesus and Lil Wayne. So let's look at this. So this is an interesting example because the population mean is known. Mu equals 11.6. And again, you don't often know this. That's usually the whole point. You take a sample and you want to say what's going on in the population. But in this case, because it's small, the mu is known. So let's take a look at this. Jesus and Lil Wayne, that'd be 14 plus 9. That's 23. And the mean of that, our X bar, Antonia's X bar, would be 11.5. So we can think about, is this statistic a good estimate of that parameter? I mean, and it is, obviously. It's as close as you can get to 11.6, taking a sample of size 2. But let's go a little further. Antonia, pick another pair.
Tiber and Paris.
Okay, me and Paris. So there's 19, right? So what is that? Is that a good estimate of 11.6? Well, let's look and see. Now, let's review. What I get for my mean depends on which random sample is chosen. And there's only, in this population, there's only 10 possible pairs that I could sample. But we can go through and we can look and see which of these are a good estimate of the population mean, which was 11.6. So we can go down the list. Which one looks pretty good? That's pretty good. That's pretty good. That seems high. That's good. That's good. That's good. That seems low. That seems high. That seems low. That seems good. And we can say, look, we take a sample, we can get a pretty close estimate to what the truth is. Remember, the parameter, the Greek letter, is the truth. And we're trying to estimate it based on our sample. But let's think for a second. How could I get a better estimate of the truth? I have this cool feature here. I can erase something. This was the lowest one that I have, 8.5. And it's the 2 worst free throw shooters in the group, me and Lil Wayne. That was my best podcast episode with him. So think about this for a second. How could I get a better estimate? Well, if I had these 2 people right here, all I need to do is add anybody else. And what happens to 8.5? It will go up. It will go closer to the truth. Because it's more likely that these low people right here, this one and this one, will get canceled out by someone who's really good at shooting free throws, like Jesus. So it should be obvious that the bigger your N, the bigger your sample size, the better estimate of the truth you will get. So you always want to get a big N so you can home in on what the truth is. So N is going to be really important when we see how spread out are these means. So take a look at this. See these numbers? I can put those numbers in some sort of graph, something like this, from say 8.5 up to 13.5, and so on. That's the sampling distribution. But if I had a bigger sample, say size 3, this distribution would be tighter because that 8.5 would get pulled up a little bit. So this is important, the sample size. Now, there's one other really important element which dictates how much error or variability there'll be around an estimate like this. And I used to take, this is my daughter Apollonia here. I used to take my kids to an indoor playground at the YMCA. And this indoor playground was basically me and like 500 moms sitting around drinking Dunkin' Donuts while all these kids ran around. And I'd just done this free throw example for a class. And so this was Pony when she was about 2 years old. I gave her this basketball. I said, Pony, let's see how many free throws you can make. So she goes to the free throw line, which is 15 feet away from the rim, which is 10 feet high. And she grabs this basketball and she takes the basketball and she goes like this. And she's just like, she just throws it. No chance. It's zero chance of going in. If I give it to her again, no chance. Give it to her again, no chance. Guess how many free throws she made? 0. So I randomly grab another kid who's at this thing, just reach out and grab him. It's some kid, Caden or Braden or Jaden or something. And I put him on the line. Guess how many he makes? 0. I grab another random kid. Guess how many she makes? 0. And it becomes very obvious pretty quickly that how many little kids do you need to get an estimate of how well little kids shoot free throws? You only need 1. Because as soon as you've seen the first one, you've seen them all. And that's because the variability of the population is not very big. It's not very big. Think about a country like the US where we have tremendous disparities in wealth. How many Americans do you need to sample to get the average income? Well, a lot, because you're going to have a lot of people cancel each other out. But what about a country that had a very equitable distribution of wealth? How about a country where everybody made the exact same amount? How many do you need to sample? That N goes down. So I think it's common sense that the bigger the sample size we have, the better estimate you get, the tighter of a spread that you get. And also how much the population itself varies also drives how spread out those means are going to be. We'll talk more about this and we'll add the idea of the shape of this distribution in a little bit.